Dear all, in this video we are going to see about the time response of a second order system. The block diagram of a second order system is given as shown in the figure. It is a unit feedback system, and here you know how to find out the transfer function of any closed loop system. It is given as g of s divided by 1 plus g of s h of s. So here the block value is given as omega n square divided by s into s plus 2 zeta omega n. This is the standard second order open loop transfer function. I am substituting this value in the closed loop transfer function equation. When I substitute it and simplify the equation, I get the value to be the transfer function of closed loop function equation is obtained to be omega n square divided by s square plus 2 zeta omega ns plus omega n square. You can see here. So here this omega n square is called as the undamped natural frequency. It is a frequency value. The name of omega n is named as undamped natural frequency, and zeta is called as damping ratio. These two are new terms what you are learning over here. Zeta is called as damping ratio. So now you can understand that the power of s in the denominator is equal to 2, and hence this is a second order system. So what we are going to do now is that we are going to find out the time response analysis, or we are going to perform the time domains analysis for a second order system. So from, in the transfer function, the denominator is called as the characteristic equation. So the denominator of the transfer function, what we have seen in the previous slide, is s square plus 2 zeta omega ns plus omega n square is equal to 0. Now I try to determine the roots of this equation using the mathematical formula. So this is a second order equation. For this I can use the mathematical expression, that is minus b plus or minus square root of b square minus 4ac divided by 2a. The same formula is used here to find out the roots of the characteristic equation. So here in this equation, b is 2 zeta omega n, stands for here b. So I put minus b plus or minus square root of b square, that is 2 zeta omega n whole square, minus 4 AC. A is equal to 1, C is omega n square. I substitute over here, divided by 2 into A. I simplify this expression. On simplification, I get the roots to be minus zeta omega n plus or minus omega n square root of zeta square minus 1. So you can understand there are two roots present. Plus stands for one root and minus stands for the second root. So this is the roots obtained for the transfer function of a second order system. So from the roots, what I can do here is that I can substitute various values of zeta, and I can get to know what will be the values of the roots. So zeta, already explained, zeta stands for damping ratio. This zeta stands for damping ratio. So I can substitute zeta to be various values, and I can get the values of the roots to be present. The first case, what I do here is that I substitute zeta equal to 0. You can see here, substitute zeta equal to 0 in the expression. When I substitute zeta equal to 0, what you'll get here is that the first term will become 0, second term you'll get plus or minus omega n. So here, and my root of minus is there, minus 1 plus or minus omega n, which means that you'll have two roots to be present and both the roots will be imaginary. How do I say both the roots to be imaginary is that square root of minus 1 will be equal to j. So you know that square root of minus 1 will be equal to j. So this is an imaginary value. So when I substitute here, square root of minus 1 will be present. You get it to be j here. So two roots will be there, plus j and minus j omega n. Both the roots. So hence it is said to be imaginary. The second case is that I substitute zeta equal to 1 in the same equation. When I substitute zeta equal to 1, the second term will become 0. You'll have only the first term to be present. So that is minus zeta omega n. So you'll have two roots, both the roots will have the same value. The third case is that I substitute zeta is greater than 1. When I substitute zeta is greater than 1, the second part will have a positive value. When it has a positive value, the roots will be real, but they may not be equal. Okay. And the last case, I substitute zeta is falls between 0 to 1. When zeta falls between 0 to 1, it is less than 1. So in this equation, when I substitute zeta to be less than 1, this part will be imaginary. So you will get a complex root. You'll have this part and this will be plus or minus j into omega n you'll have a complex part. When you have a complex part, the roots are complex conjugate. Okay, so these are the different types of root. What do I get when I substitute zeta to be of different values? So for the transfer function, closed loop transfer function, what I'm going to do now is that I'm going to find out the response, C of t. I'm going to get the C of t of the transfer function. So here, C of s is the Laplace transform of the output signal, R of s is the Laplace transform of the input signal, omega n is the natural frequency, and zeta is called as the damping ratio. We have already seen all those things. Now let me see the step response of a second order system. So step response means I'm going to give an input of a step value and I'm going to find out the response. Step value is R of s is equal to 1 by s. So the first case I'm going to take zeta is equal to 0. Substitute in the transfer function. When I substitute in the transfer function, you'll get C of s by R of s is equal to omega n square divided by s square plus omega n square because zeta becomes 0. So here again, I take C of s, I bring the R of s to the other side, plus omega n square divided by s square plus omega n square into R of s. Now, instead of R of s, I'm going to substitute 1 by s, which is seen over here. When I substitute 1 by s, I'm going to simplify this expression. What we have done for first order system, the same thing I'm going to do it over here. I'm going to apply partial fraction method. So on applying partial fraction method, I split up the equation. We'll have a by s plus bs plus c divided by s square plus omega n square. I try to simplify this expression and find out the values of a, b and c. On substituting s equal to 0, I get the value of a equal to 1. Equating s square component on both sides, I get b is equal to minus 1. And equating s value, I get c equal to 0. So I substitute the values obtained in the expression. C of s becomes 1 by s plus of minus 1 into s divided by s square plus omega n square. So now this is very important. So now I'm going to take, my ultimate aim is that I have to find out inverse Laplace. So I'm going to take C of t. C of t is obtained by taking inverse Laplace for the expression because this is time domain specific, time domain response. So I have to convert this into time. To convert this into time, I have to convert the frequency into time with the help of inverse Laplace. So we know that L inverse is equal to S divided by S square plus A square is equal to cos A of t. So the value I substitute, I take inverse Laplace. If I substitute 1 by S inverse is 1 and from the value of L inverse, this value I'm going to substitute over here. So what do you get? Minus cos omega n into t. When I look over this expression, I can see that there is no exponential decay term to be present. So my output does not decay. It will be a cos wave. So since cos is present, this will be a cosine wave and the wave will be of constant amplitude. So this is the response that is obtained for the system with the value of zeta equal to 0. Okay. Next one is I take zeta equal to 1. The same procedure I have to follow. To find out my ultimate aim is I have to find out C of t. I'm going to find out the same procedure. I'm going to adopt the same procedure. I substitute delta equal to 1 in the transfer function. When delta is substituted to equal to 1, I can simplify this expression as this omega n square divided by s plus z omega n whole square into r of s. I take it for step input, so substitute r of s is equal to 1 by s in the above expression. So again I do the partial fraction method. So For partial fraction method, you can split this into three terms. One is a by s, the second one is b divided by s plus omega n, and the third term is c divided by s plus omega n whole square. I find out the values of a, b and c by substituting various values for s. So I get it to be a equal to 1, b equal to minus 1 and c equal to minus omega n. Substituting the values in the C of S equation and taking inverse Laplace transform, I get it as 1 minus e power minus omega n into t minus omega n t e power minus omega into t into u of t. So what you can see here is that you do not have any cosine term or sine term to be present. So the expression does not have any oscillatory waveform. It has only a decaying waveform. Decaying e power is there. So e power minus is there, which means that the waveform is decaying. So you got only a decaying part and does not have any sinusoidal part to be present. So the unit step response of the second order system will try to reach the step input in the steady state without any decaying portion. So this is for zeta equal to 1. The third case is I substitute the values of zeta to be less than or lies between 0 to 1. So this is the case most prevalent in all the systems, and so here when I substitute, you can see here the simplification what is done in the system. S square plus 2s zeta omega n plus zeta omega n square. I'm trying to group the equation. So I add zeta omega n whole square to be a part. Since I'm adding a new part, I'm subtracting the same in the equation. So when I add and subtract, I can group this expression as s plus zeta omega n whole square plus of omega n square. I try to take omega n common in both the expression. Both these expression I can take omega n common. So when I take omega n common, I can make it as omega n square into square root of 1 minus zeta square. So now I substitute this value in my transfer function equation. C of s by R of s will become omega n square divided by s plus zeta omega n whole square plus of omega n square into 1 minus zeta square. So now I do the step response analysis. I first supply the step value. So step value R of s is equal to 1 by s. I apply it over here. Then I do partial fraction with the same procedure I'm going to adapt. I do partial fraction method. So omega n square divided by the equation will be equal to a by s plus, since this term has s into s plus some term, so I have to split it as bs plus c. So s plus zeta omega n whole square plus omega n square into 1 minus zeta square. I simplify this expression, find out the values of a, b and c. A comes to be 1, b comes to be minus 1 and c comes to be minus zeta omega n. So now what I do here is that I substitute the values of a, b and c in the expression. You can see here after substituting the expression, I again try to simplify it. What do I do here is that I split up this expression. S plus 2 zeta omega n, you can see. This is splitted as s plus zeta omega n minus of zeta omega n. This is 2 zeta omega n, I'm splitting it as 2. After this, what I'm going to do is that I'm going to group out the expression, and in the second part, you can see 1 by s is written as it is. S plus zeta omega n plus s plus zeta omega n square plus omega n square. This is written as it is. And again, here you can see I'm going to multiply zeta. Zeta is already there. So omega n, I'm going to multiply square root of 1 minus zeta square in the numerator. The same thing I'm dividing it over here. So you can see omega n into square root of 1 minus zeta square divided by square root of 1 minus zeta square. This is again for simplification. So now what do I do here is that I substitute omega n square root of 1 minus zeta square is equal to omega d. So this omega d is a new term. This is called as damped natural frequency, damped frequency. So wherever omega n square root of 1 minus zeta square is present, I substitute it by omega d. You can see first term is written as it is 1 by s. Second term, omega n square root of 1 minus zeta square is written as omega d square. Similarly, in the third term also, wherever I have that term, it is replaced by omega d. Now, I apply inverse Laplace. Now it becomes easy for me to apply inverse Laplace. On applying inverse Laplace, my expression is obtained to be 1 minus e power minus zeta omega nt cos omega dt minus zeta divided by square root of 1 minus zeta squared e power minus zeta omega nt sin omega dt into u of t. I try to again simplify this expression. So what do I get here is that if square root of 1 minus zeta square is equal to sine theta, I assume that square root of 1 minus zeta square is equal to sine theta, then zeta will be cos theta. So this is like a triangle. I try to take it like a triangle. So here, so sine theta is square root of sine theta, opposite by hypotenuse, is taken to be square root of 1 minus zeta square. Zeta will be cos theta is adjacent by hypotenuse. So this will be zeta. So this will be square root of 1 minus zeta square. So this will be square root of 1 minus zeta square. So hypotenuse will be equal to 1. Sin theta is square root of 1 minus zeta square divided by hypotenuse is 1. And cos theta is zeta divided by hypotenuse is 1. When I make this substitution, I have it to be square root of 1 minus zeta square is sin theta, cos omega dt will be as it is, and zeta will be is cos theta sin omega dt. Okay, so now this could be simplified as sin theta sin A cos B plus cos A sin B is sin A plus B. So I simplify this expression and I write it as sin A cos B. You can see sin of A plus B. My output expression C of t will be equal to 1 minus e power minus zeta omega nt divided by square root of 1 minus zeta square sin of omega dt plus theta into u of t. So this expression is the output expression of a second order system where zeta falls between 0 to 1. And this expression is followed for many of the systems because many of the systems will follow only a second order system which has the zeta value to lie between 0 to 1. So this system, when you see the output expression, you have got a sinusoidal term. So the response will have a sinusoidal part, and along with that you have got an exponential decaying part. So my response, what do I get here is that it will be like this. You will have a sinusoidal part and the sinusoidal part will be exponentially decaying. So this will be the response of the system.